Okay, in this video, I'm going to cover section 4.10, a closer look at mechanical vibrations. So this is the last section in chapter 4, um, but this section is you will see many numbers and letters and formula. So it's going to be complicated, and then maybe it's hard to understand. So I suggest you watch this video more than once. Um, so what are you gonna do? So we wanna figure out the general solution of the forced uh, mass spring system. Okay, so 4.9. In 4.9, we learn about the free mechanical vibration. It means that force function is zero function. But 4.10, so the external force function is non-zero function. So we'll see. So right here, we're going to consider the mass spring system. My second derivative plus by prime plus ky is equal to f0 times cosine gamma t. So this kind of the uh, the source function involving this sine or cosine function is called the sinusoidal function. Okay, so yeah, in particular, we're interested in the mass spring system with that source function. So now in the f0 and the gamma is non-zero constant, and then b squared is less than 4mk. So that what the it means that the system is an undamped system. So now because b squared is less than 4mk, it means that so the general solution of the homogeneous differential equation corresponding to this non-homogeneous differential equation gonna have the has the form the a times the phase amplitude form. Remember that. So which is this right there. Okay. So because the root of Ox equation of the homogeneous equation corresponding to associated with this one, that non-homogeneous differential equation should have the complex root because b squared is less than 4mk. Okay, so now the general solution by the superposition principle, general solution going to be the general solution to the homogeneous differential equation plus particular solution. So we know how to find out that for YH, the general solution to the homogeneous differential equation, we learned that in 4.9. So YH is nothing but the general solution to the free mechanical vibration model, right? So we figured out this one. Okay, but let me go over. Let me prove why YH is like this, because the YH is the general solution to the homogeneous differential equation associated with that non-homogeneous differential equation, which is this. Okay, so then the Ox equation is this, and then we solve the Ox equation. We're gonna get this one by the quadratic formula. So alpha going to be negative b over 2m. And by the way, we assume that b squared is less than 4mk, so that the discriminant is what? Going to be the negative. So r going to be a complex number. So alpha is a negative b over 2m, which is a real part, and the imaginary part is this. Okay. So you see that the reason that I just switched the b squared for mk, because once we take out the complex unit I, we're going to get this. Then we can get two solutions, e to the alpha t cosine beta t, e to the alpha t sine beta t. Now then our general solution is going to be this. Okay, then we can and then we simplify this one to the phase amplitude form, right? So A is the square root of C1, square root of C2 square. Keep in mind this. What is C1? C1 is the what? The A times sine beta t, and the C2 is right here. So C1 is what? A times sine beta t, and then C2 is A times cosine beta t. Okay, so keep in mind this. So now, okay, so then where A is a square root C1 squared plus C2 squared, and then tangent pi gonna be C1 over C2, and the pi is a phase angle, right? Okay, so and then yes, the beta is this. Okay, I mean the imaging part. So now, I mean if you don't get that why this one can be expressed like this, and then this form is called the amplitude uh, phase amplitude form. Then again, just look, please watch the previous lecture, okay, covering 4.9. Now, so we got the YH, right? So this is YH. The what about the YP? YP is this. Let's see that. Where that comes from? Um, we apply the method of undetermined coefficient. Okay, so we'll see. So to determine the YP, we can use the method of undetermined coefficient, as I told you. So then what? The the form of the particular solution is determined by the type of the what? Source function, right? So here the source function is f0, I mean constant times, and the cosine function. So since cosine is involved, the form of a particular solution must be this right here. And then definitely n must be 0 because what? There is no polynomials involved. Okay, so n must be 0, right? And then also alpha must be 0, right? Because no exponential term in the source function. So n must be 0, and the alpha must be 0. Okay, so cosine is the beta must be gamma, right? Okay, so now then we to figure out the s, we're gonna compare the what? The complex root of the Ox equation with the alpha and beta. Okay, so in the particular solution, alpha plus beta I must be gamma, right? Because alpha is 0, right? And then beta is gamma, right? So it should be, this is gamma I, right? Sorry. And then now then the complex root of the Ox equation is this. So definitely this is not equal to gamma times I. So S must be 0. So we got the reduce the form of the particular solution is like this, right? And then we figure out the A1 and A2 by substituting this solution to the differential equation. Okay. So now then, see. So do find out yp prime, yp double prime, and then plug them into the differential equation, and then we're gonna get the system of algebraic equation. Okay. So then we got this. A1 is this. A2 is this. Okay. Right. I know it looks like complicated, but yeah, we're gonna simplify that. So a particular solution gonna be, see that? We're gonna plug in A1, this one, and this one. We're gonna plug them into the well, into here, right there, right here. Okay. So now then we're gonna get this. Since as you can see that A1 and A2, F0 over this one is that fraction is a common factor of A1 and A2. So we can factor that out. Okay. So now then K minus M gamma square cosine plus B gamma sine gamma t. All right, so this one can be expressed is the phase amplitude form. Why? Because, let me see, right here. We're considering that this one is the what, C1, and this considers C2. Okay. Then the way we apply the way we get the phase amplitude form from here. Which one? Oh yeah, right here. Okay. So it's similar to the way we get the phase amplitude form. So we can get the we can figure out the amplitude, which is square root of C1 squared plus C2 squared. Okay. All right. And then times sine gamma t plus pi. Pi is the phase angle. Pi can be what uh, um, can be obtained by this one. Tangent theta is equal to A1 over A2. Okay, what's A1? A1 is this is A1. A2 is this. Okay, but uh, you can say actually what the K tangent theta is equal to K minus M gamma square over B gamma. Okay, all right, but this is nothing but this. Okay, why? Because A1, A2 have have common factor F0 over this. So when you do fraction, that common factor going to be canceled out, right? So uh, this is nothing but this. Anyway, so excuse me. So we figured out the particular solution, and then we simplify the particular solution like this. Okay, and then we apply the superposition principle. We can get general solution, which is this. Okay, that's the what? The general solution to the homogeneous differential equation. I mean, free mechanical vibration model. This is a particular solution to the what forced mechanical vibration model with the sinusoidal sourcing function, external force. Okay. So here the one assumption is b squared is less than 4mk. Okay. And then here a is the square of c1 squared plus c2 squared. Okay. So c1 and c2 are the well, unknown constants of unknown the unknown constants of integration. I'm sorry. Okay. So this is the first objective, the figuring out the general solution to the the forced mechanical vibration with the sinusoidal external force. That's the first objective. Second goal is to analyze this one. Okay. So we want to figure out the behavior of the general solution. Okay. And then we want to figure out the what if B is really small, and then what is how does the gamma, what is the gamma? Gamma is actually what? The frequency of the external force, right? Sourcing function. You see the key mind, you see? So what is the gamma? Gamma is the frequency of the sourcing function, or you can say the frequency of the external force. So I want to figure out how does this gamma affect on the behavior of this, okay? And then so what's the relation among the gamma and B and M and K? Okay, so first one, as you can see that see the first term, which is the general solution to the the homogeneous differential equation. There is the exponential term is involved, and then that exponential term is decreasing function because the B and M, B over 2m positive, right? And then so negative B over 2m is a negative. So that exponential term is decreasing. So t approach increase, that term will approach zero. Okay, And then see second term doesn't is not involved the exponential term. Okay, so y of z approach what the y of p as t approaches infinity. So YH represent damped oscillation and depends on the parameter of the system and the initial condition. Yeah, so since the YH, as you can see that these two terms have the sine function involved. So definitely the YH represent the the motion of the oscillation, oscillatory motion of oscillation, yes. And then the parameters of system in this one depends on parameters on this of the system. Yeah, we see that a lot of parameters m, k, b, and gamma involved in the solution, right? And then that's what I told you. So exponential term approaches zero as t approaches infinity. So consequently YH is referred to as the transient part. What's the transient part? uh this one, transient part, because eventually it will disappear as t approaches infinity. So yp is the offspring of the external forcing function. Yes. Oh, let me see that. So and then yp is a sinusoid with an angular frequency gamma. Yes. So as the transient term dies off, the motion yg becomes essentially that of the second term yp. Okay, that term is called the steady state solution. Okay. So in the general solution to the free mechanical vibration with the sinusoidal external force, the first term, which is the general solution to the homogeneous differential equation, is transient term. It will disappear. And the second term, particular solution to the non-homogeneous differential equation mathematics, is the what? Steady state solution. Okay. So this is roughly, I mean this graph of YAT and general solution and the particular solution. As you can see that particular solution is just is wave function, right? Okay, but YT first, wave the was a wave function. It was a we see that oscillation motion of the oscillation, but the amplitude decreased because of exponential term, and eventually, what desynchronized with the to the YP. As you can see that. Okay, so now then, next the observation. So the factor 1 over gamma k minus m times gamma square plus b squared gamma squared, that is referred to as the frequency gain or gain factor. So we're going to focus on the analysis of this one. Okay, what is this? Where that comes from? This comes from what? Right there. In a particular solution, okay? Just take out the f0, then we get the 1 over this. Okay? You see that? Okay? So that is called the frequency gain or gain factor because it represents, so this one represents what? Ratio of the magnitude of the sinusoidal response to that of the input force. Okay? So input force is the what? F0. And then this one will determine what? The magnitude. Okay? This will determine the ratio of the magnitude of the sinus, the cosine function, cosine function in the external force, right? Okay, and then gain factor is, you can see that k. You see that k, and k is what? Why is it k? K is a spring constant. M is the mass. B is a damping constant, right? So gamma is the only the variable. So this factor depends on the frequency gamma. Okay, and then what's the gamma? Gamma is the unit of gamma is length of force. Okay, so now we see example. We see example 1. Let me see. Give me a second. Okay, so here's the example one in textbook. So 10 kilo, here's a problem. A 10 kilogram mass is attached to a spring with a stiffness K is 49 Newton per meter. At time t equals 0, an external force F of t is 20 times cosine 40 Newton is applied to the system. Then the damping constant for the system is 3 Newton second per meter. To determine the state solution for the system. So state solution means what? The particular solution, right? So anyway, let's figure out the differential equation, the model. So we're gonna substitute the all the parameters into the the non-homogeneous differential equation. So then we'll get this. Okay, 10 times a y dot prime plus 3 times y prime. It was because the problem says the damping constant is 3. Okay, so and the 49y is equal to 20 times cosine 40. Okay, so definitely yt is represent displacement from the equilibrium of the mass at time t. So then you see to find out yp, what's the yp here? So give me a second. So yp, I mean steady state solution. Solution is what? This is yp of t. The formula is f0 over k minus m gamma square and a square plus b square gamma square, right? Okay, so in the problem f0 is given by 20, and then stiffness, which is spring constant, is a 49, and then mass is the excuse me, the mass is 10, right? Okay, and then b is 3. Okay, and the gamma is what? Let's see, gamma is, give me a second. The problem says that gamma is 4. Yeah, gamma is 4. Gamma equals 4. So then what? Then, but combining these numbers and substituting these numbers into the fraction yp, we're gonna get the 20 over the square root. Okay, the 49 minus 160 squared plus 9 times 16. See? Okay, and then sine times the sine. Oh, yeah, I missed that. Sine gamma t plus page angle theta, right? Times, this fraction times what? Sine, and then 4t plus theta, right? Okay. But now, how can you find the theta? Theta is what? Tangent theta is equal to what? C1 over C2, isn't it? Okay. So, well, in this case, A1 over A2, right? And then, remember that A1 is the then we need to figure out the what? The which quadrant this data belong to, right? Then we figure out the to figure out which quadrant data belong to, we need to figure out the sign of A1 and A2, right? Okay, so A1 is the what? Here A1. So now A1 is, what was this? K minus M gamma square, and the A2 is B times gamma. Okay. So which is what? This is equal to nothing but what? 49 minus 160, right? Then B gamma is what? 3 times gamma, which is 12. So A2 is positive, and the A1 is less than 0, negative, right? So which is here. Is it? So now then, what? The theta must be what? Must be between 3 pi over 2 to 2 pi, right? 2 pi. Okay. Okay. Then what's the so now then give me a second. So now it should be this one, or the I mean, so theta must be between 3 pi over 2 and 2 pi, or between negative pi over 2 to 0. Is it? Okay. So now the tangent, okay, so plug in the 49 minus 160 into A, and then 12 into A2, then tangent theta is equal to what? Negative 9.25, and then theta is equal to arctangent negative 9.25. Then this is approximately negative 1.46. Okay. So it means negative 1.46 must be what? Between negative pi over 2 to 0. It makes sense. So finally, we got this. Yp is equal to, what is this? The computing this one, okay, just put this fraction into calculator, you will get this 0.18, okay, times sine 4t and then minus 1.46. Okay, so we got this. Right. So now then, give me a second. So this is example 1. Okay, so but back to here. So now let's see example 1. See here. Okay. So as you can see that in general, so the amplitude of the state-state solution, I mean, in this example, what's the amplitude of state-state solution? 0.18. How we got this? Where that number comes from? This one, right? From here. Okay. So I told you, the second objective is to figure out the is to do analysis of this one, this term. Okay, so this is amplitude of the state-state solution. So now, in general, the amplitude of state-state solution to that differential equation depends on the angular frequency gamma, yes, of the forcing function, and is given by this one. Yeah. So now, what that means, we express the amplitude of the state-state solution as what? F0 times m of gamma, because the denominators k, m, b are the are just given, fixed, right? So gamma is, we consider gamma as the gamma is the only unknown constant, unknown variable, kind of. So we consider this one as a function of gamma. Okay, so that one is called the frequency gain. It's called frequency gain, right? Frequency gain. Okay, we learned it, right, in the previous page, right? So now, look at this here. Here's note for a given system. It is often of interest to know how this system reacts to sinusoidal input of various frequencies. Gamma is a variable. Okay, for this, so what that means, we want to figure out how the gamma effect on the sinusoidal behavior of the solution. That's what we want to figure out. This is the second objective. Okay, so for this purpose, the graph of the gain m gamma, called the frequency response curve, or resonance curve. Okay, resonance curve. So let's see. First one, to figure out, so I want to figure out the behavior of M gamma. Then what we have to do? We go back to calculus 1. We need to figure out the critical values, find out maximum, local minimum, absolute maximum, absolute minimum, right? So to find, I'm going to find the critical values. Then we have to find out the derivative of the M of gamma with respect to gamma, right? Okay, so the take a derivative discount with respect to gamma, we're gonna get this. I know it's complicated, but that totally you don't have to memorize it. Okay, so here, then we set this equals 0 to find the critical value. Then we're gonna get two solutions: gamma equals 0, or gamma is equal to square root k over m minus b squared over 2m squared. Okay, let's denote this one as gamma sub r. Okay, but gamma equals r, this kind of trivial solution, right? But okay, anyway, so we got two critical values, right? So keep in mind this. So now that we can think about two cases. So overdamped or critical damped, or case 2, underdamped. Okay, but definitely we are interested in this case, underdamped. Okay, so now then, but okay, so let's see this case. B squared is greater than or equals 4mk or greater than 2mk. It means that Aux equation gonna have two distinct root, or I mean simple roots or double root, right? So then the k over m minus b squared over 2m squared. What is this? This is the one of the critical value, right? Remember that right there. This one. And this gonna be what? This is gonna be the complex root, because the k over m is equal to 2mk over 2m squared. Therefore, this fraction is less than b squared over 2m squared. Why? Because b squared is greater than or equals 4mk and the greater than 2mk. So 2mk, this guy is what? Less than b squared. Okay? So gamma r going to be square root of negative number, which is complex number. So the m prime equals 0, gonna have what? The solution 0 only, right? Okay. And then we know that m of gamma is decreasing function. Why m of gamma is decreasing function? Because let me see, m of gamma right there. So you see that for fixed k and b, if gamma is increased, then denominator is increased, right? While the numerator is fixed as 1. So this function decreasing function, right? So the what? The m of gamma is decreasing function, and the if gamma approaches 0, approaches infinity, then the frequency gain approaches 0. Okay, frequency gain approaches 0, and then m of 0 is 1 over k. So this is the maximum value of the frequency gain. We can get this one when what? Gamma is 0. Okay, the case 2, and then we don't see any okay, I'm sorry. The second case, underdamped. What does that mean, underdamped? Underdamped means that the solution has the sinusoidal behavior. Okay, so it means that the b squared is less than 2mk. Okay, so now then gamma r going to be positive real number, and the gamma m, the frequency gain, has a maximum value at gamma r. Okay, let's see. Okay, substituting gamma r into m, that will give this. So this is the maximum value of m. Okay, so it is occurred at gamma is equal to gamma r. Okay, and the gamma r over 2 pi is called the resonance frequency for the system, and then when the system is simulated by an external force at this frequency, it is said to be at resonance. Okay, so now keep in mind this, the resonance frequency. Okay, so resonance frequency. Now, all right. So to illustrate the effect of the damping constant B on the resonance curve, we consider in which m, k, are m equals k equals 1. Okay, both m and k are 1. All right. Okay, out of blue, what we want to figure out the effect of the damping constant B. We'll see. We'll see, right? So now we'll see. First of all, we're gonna plug in 1 into m and k. Then what are we gonna get? Let's see. Oh, give me a second. The frequency, the definition of frequency gain is this, right? So plug in 1 into k, plug in 1 into m. Then we're gonna get 1 minus gamma square over square plus b square times gamma square. That's gonna be inside of radical in the denominator, right? So we get this, and then this one also has the what? The maximum at gamma r, gamma sub r, which is this, and then substituting 1 into m and k, we're gonna get this. So now, then the resonance frequency is gamma r over 2 pi, which is this. Okay, so now let's just look at this gamma r. If b approaches 0, then gamma r approaches 1, right? Okay, okay. And there is a b approaches 0, the frequency gain approaches what? If b approaches 0, then approaches 0. Okay, if b approaches 0, what happens? The gamma r approaches 1. So b approaches 0, then b squared times gamma squared going to approach, b squared times gamma squared approaches 0, and then gamma what? And b approaches 0. Then what? Sorry. Then the frequency gain approaches 1 over square root 1 minus gamma square, which is this. And then if gamma r approach 1, b approaches 0, then gamma r approaches 1. Then when you plug in gamma r into the frequency gain, then this one approaches what? Infinity. Why? Because b approaches 0 means the second term approaches 0, right? And then plug in gamma r approaching 1 into gamma, then 1 minus gamma squared approaches 0. So frequency gain approaches infinity. Okay. But what is it? Frequency gain. Frequency gain is what? The ratio of the magnitude of the what? The sinusoidal sourcing function, right? Sinusoidal the external force. Is it? Okay. So the magnitude of the external force and the sinusoidal external force approach infinity as gamma r approaches 1, which means that b approaches 0. Okay. So let me generalize this. So this is really important. Listen carefully. So gamma r, actually, you see that? Gamma r is this, right? Okay. So for any m and k, for any m and k satisfying this condition under damped, then gamma r approach what? Square root k over m as b approaches 0. If b approaches 0, then this fraction approaches 0. So k over m gonna be left. So gamma r is approach square root k over m. But square root k over m is what? Omega. Is it? We haven't seen this omega in the what? The free mechanical vibration for section 4.9. You see? You see? That was the what? The natural frequency. What? Actually, what? Give me a second. So the natural frequency, the omega over 2 pi is natural frequency, I'm sorry, or 2 pi, yes. Okay, as b approaches 0. And then the frequency gain approaches this as b approaches 0, yes. Okay, and then the gamma r approach omega, the frequency gain approach infinity. Does it make sense? Why? R, I'm sorry, gamma r. Okay, why? Because you get substituting gamma r into gamma, when it gets then gamma square gonna be just k over m. Then k minus m times k over m gonna be what? 0. Okay, so this denominator approaches 0, so that's why m over gamma r approaches infinity. Okay, so now then, okay, so now the what does that mean? Here we can see that it means that what? As b approaches 0, the maximum magnitude of the frequency gain increase, and the resonance frequency gamma r over 2 pi for the damped system approach the natural frequency for the what? For the undamped system. Okay, so thus if the damping constant b is very small, okay, the system is subject to large oscillations when the forcing function has a frequency. What does that mean? Forcing function has a frequency. Forcing function is f0 times cosine gamma t, right? We assume that, right? And the gamma, that's the frequency of the forcing function. That near the resonance frequency is the gamma r over 2 pi, but just ignore the over 2 pi, okay? So resonance frequency gamma r is near, I mean, that one, a frequency near the resonance frequency. So it means that gamma r, which is approximate, which is near the omega. Why? Because b is really small. Remember that? If b approaches 0, b is really small, then what? Gamma r approaches omega. So this is approximately omega. Okay, so b, the constant b is really small, then the resonance frequency approaches the natural frequency on the empty system. And then the gamma, this gamma, which is frequency in the forcing function, near the gamma r, which means that the frequency of forcing function near the what? The natural frequency. Then the system will have the large oscillation. Why? You see that? Why large oscillation? Why we're gonna get the large oscillation? Because the frequency gain approaches infinity. So you see, one second. So look at the graph here. This graph, this is a figure of the frequency response curves. Frequency response curve is nothing but graph of the frequency gain, m of gamma, okay, for the various value of b, okay. So gamma, so here we assume that k, I mean stiffness and the mass equals 1, okay, so that the gamma, I mean b approach, you see that b is getting smaller and smaller, so b approaches 0, then the frequency gain gonna have a maximum value at at around the 1 as gamma. It makes sense, right? Okay, see that. So what's the example of this? Example is this. Here, the excuse me, Tacoma Narrows Bridge. So I'm not gonna explain this one in detail, but please read this article, okay, by yourself. So see what happened. So let me give this. See that? This is showing the how the small the if the small damping constant cause the large vibrations. Okay, certain the frequency, I mean the gamma, I mean the frequency of the forcing function is the near the resonance frequency, under the assumption that B is really small, they wouldn't get the large vibrations that cause the collapse in this yeah. So that's the example of the Takamine example of the resonance. Let me see, resonance. Okay, so please look at this. Let's see. All right, so I told you, as you can see that this section is a lot, harder than other sections. So please, the read the textbooks and then watch this lecture video more than once. Okay. So and then if you have any questions, just let me know. Okay. So let me stop here.